Hello my dear friends, welcome to my YouTube channel. Myself Dattu Patel, Assistant Professor from LJIT. Earlier lecture we are already discussed about the eigenvalues and eigenvectors. Today's session we are going to discuss about the Cayley-Hamilton theorem. Let's see. Firstly, what is Cayley-Hamilton theorem or a statement? Then every square matrix satisfies its own characteristic equations. For example, if minus 1 raised to n lambda raised to n plus a1 lambda raised to n minus 1 plus a2 lambda raised to n minus 2 and so on plus an minus 1 lambda plus an equal to 0. That is the characteristic equation of the n cross n for the given matrix capital A. Then replace the lambda as a given matrix capital A and that will give you minus 1 raised to n a raised to n plus a1 a raised to n minus 1 plus a2 a raised to n minus 2 and so on plus an minus 1 a plus an into I, where I indicated by the identity matrices is equal to 0, where 0 is nothing but the 0 matrices or a null matrices of the order n. Here we satisfy our polynomial equations in form of matrices is equal to 0. That is exactly statement of the Cayley-Hamilton theorem. Let's see what example. Verify the Cayley-Hamilton theorem for the following matrix. Hence, find the A inverse and A raised to 4, where A equal to 2 minus 1 1, minus 1 2 minus 1, 1 minus 1 2. Then firstly, here our matrix is in form of order 3, means 3 cross 3 matrices, and for that we have to find the characteristic equations, and that is determinant of A minus lambda I equal to 0. Then in determinant 2 minus lambda minus 1 1 minus 1 2 minus lambda minus 1 1 minus 1 2 minus lambda equal to 0. Before the verification of the Cayley-Hamilton theorem, firstly we have to finding the S1 S2 S3 and substituting the S1 S2 S3 in our characteristic equations of the order 3, that is lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. Here S1 is nothing but the sum of principal diagonal elements of the A, that is trace of matrix A. Here our diagonal elements are 2 2 2, then adding of that diagonal elements, that is 2 plus 2 plus 2, that will give you 6. Similarly for the S2, S2 is nothing but the sum of minors of principal diagonal elements of given matrix, that is minors of 2 or minors of A11 position, minors of A22 position and minors of A33 position. That will give you 2 minus 1 minus 1 2 plus 2 1 1 2 plus 2 minus 1 minus 1 2. Now simplified 8, that will give you 4 minus 1 plus 4 minus 1 plus 4 minus 1. That means 3 plus 3 plus 3 is equal to 9. That is the exactly value of S2. Now S3 is nothing but the determinant of given matrix, that is 2 minus 1 1 minus 1 2 minus 1 1 minus 2 2. Here 2 into minors of 2, that is 2 into 4 minus 1 plus 1 into minors of 1, that is minus 2 plus 1 plus 1 into minors of 1, that is 1 minus 2, and simplified 8, that will give you 4. Now substituting the values of S1 S2 S3 in our characteristic equations of the lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. For the putting the values of S1 S2 S3, that will give you lambda cube minus 6 lambda square plus 9 lambda minus 4 equal to 0. Here no need to find the values of eigen, or no need to find the values of lambda or eigenvalues. Here we have to verify the Cayley-Hamilton theorem. For that, replace the lambda as a capital A, where A indicated by the our matrices. That will give you a cube minus 6x square plus 9a minus 4i equal to 0. That is our equation number 1. We have to verify the Cayley-Hamilton theorem. For that, firstly, here we have the term a cube and a square, and a which is already given in the question. Then finding the a square and a cube, and substituting the values of a square, a cube, a in this equation 1 in LHS portion, and simplified 8, and we get the null matrix. If it is null matrix, then verify the Cayley-Hamilton theorem. For the verified, Firstly, we have to finding the a square. A square is nothing but the a into a. Then substituting the values of a, that is 2 minus 1 1, minus 1 2 minus 1 1 minus 1 2 into again a 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. Now for the matrix multiplication, first row first column, first row second column, first row third column, second row first column, second row second column, second row third column. Similarly third row first column, third row second column, third row third column. Likewise that. Then first row first column, then 2 into 2 4, plus minus 1 into minus 1, that is 1, plus 1 into 1 means 4 plus 1 plus 1, that is 6, which is written in first value, means A11 position. Similarly first row second column, then 2 into minus 1, that is minus 2, minus 1 into 2, that is minus 2, 1 into minus 1, that is minus 1, means minus 2 minus 2 minus 1, that is minus 5. Likewise that we get the values of a square, that is 6 minus 5 5, minus 5 6, minus 5 5, minus 5 6, that is exactly values of a square. Similarly we can find the a cube. A cube is a square into a. Now substituting the values of a square into a, and likewise that similarly a square, first row first column, first row second column, first row third column, etc., which is already learned in 11-12 science for the matrix multiplication, and that will give you 22 minus 21 21 in second row, minus 21 22 minus 21 in third row, 21 minus 21 22, that is the values of a3. Now for the verifications of the Cayley-Hamilton theorem, substituting these values of a cube, a square, a in our characteristic equations or Cayley-Hamilton equations, that is a cube minus 6a square plus 9a minus 4. Now values of a cube, that is 22 minus 21 21 minus 21 22 minus 21 in third row, 21 minus 21 22 minus 6 into a square. Then whatever the values of a square, multiply with 6, means each and every values of a square which is multiplied with 6, that will give you 36 minus 30 30 minus 30 36 minus 30 30 minus 30 36 plus 9 into a, means each and every elements of the given matrix which is multiplied with 9, that will give you 18 minus 9 9 minus 9 18 minus 9 9 minus 9 18 minus 4 into I. Then here I, that is our identity matrices, that is 4 0 0 0 4 0 0 0 4. Now simplified it and adding or subtract it, that will give you 0 0 0 0 0 0 0 0 0, that is our null matrices. That is exactly we have to find. Hence verify the Cayley-Hamilton theorem, means LHS equal to RHS, means a cube minus 6x square plus 9a minus 4i equal to 0. Then the matrix A is satisfy its own characteristic equation. That is the statement of Cayley-Hamilton theorem. Hence we can say that Cayley-Hamilton theorem is verified. Now let's see for the finding the A inverse. For that, multiplying by A inverse of the equation number 1, that is A inverse into a cube minus 6a square plus 9a minus 4i equal to 0, and simplified 8, that will give you a square minus 6a plus 9a into a inverse, that is 1. 1 means identity matrix. Then we can write plus 9i minus I into a inverse, that is minus 4 into a inverse equal to 0. We have to finding the a inverse, then making the subject as a for a inverse, that will give you for a inverse equal to a square minus 6a plus 9i. We have already values of a square and a, then substituting these values of a square and a into 6, means multiplying a with 6, and that will give you 6 minus 5 5, minus 5 6, minus 5 5 minus 5 6, minus 12 minus 6 6, minus 6 12, minus 6 6, minus 6 12, plus 9 into identity matrix, means 9 0 0 0 9 0 0 0 9. Simplified 8, that will give you 3 1 minus 1 1 3 1 minus 1 1 3, that is the for a inverse. Now making the subject as a inverse equal to 1 by 4 into 3 1 minus 1 1 3 1 minus 1 1 3, that is exactly a inverse. Here we can also find the inverse by the Gauss-Jordan method or a determinant method. In this example, we have to find the with the help of Cayley-Hamilton theorem, finding the A inverse and A raised to 4. Now, for the finding the A raised to 4, multiplying the equation number 1 by A, then we get A into A cube minus 6x square plus 9a minus 4i equal to 0. Then multiplying with A, then A raised to 4 minus 6a cube plus 9a square minus 4a equal to 0. Making the subject as a raised to 4, that will give you 6a cube minus 9a square plus 4a. Here we have the values of a cube and a square, and a, substituting these values of a cube, a square and a, that will give you 132 minus 126, 126. In second row, minus 126, 132 minus 126, 126 minus 126, 132 minus 54 minus 45, 45. In second row, minus 45, 54 minus 45. In third row, 45 minus 45, 54 plus 8 minus 4, 4 minus 4, 8 minus 4, 4 minus 4, 8. Simplified this equation, means adding or subtraction, that will give you, here we adding or subtraction by element by element, means first matrix has a A11 position, second matrix has a A11 position, third matrix has a A11 position. That means 132 minus 54 plus 8, that will give you 86. Similarly, minus 126 minus plus 45 minus 4, that will give you minus 85, and so on. Then our matrices A4 is 86 minus 85, 85. In second row, minus 85, 86 minus 85. In third row, 85 minus 85, 86. That is exactly A raised to 4. Now similarly, we can find the another example. Find the characteristic equations of the given matrix A equal to 2, 1, 1, 0, 1, 0, 1, 1, 2, and hence find the matrix represented by A raised to 8 minus 5A raised to 7 plus 7A raised to 6 minus 3A raised to 5 plus A raised to 4 minus 5A cube plus 8A square minus 2A plus I. Here our matrix which is represented in form of polynomial form, in highest power, which is A raised to 8. We cannot go for directly finding the A square, A cube, A raised to 4 and so on, substituting it and simplified it. It may become very lengthy. For that, with the help of Cayley-Hamilton theorem, we can find such kind of long polynomials form of the given matrices, or our matrix which is represented in form of long polynomial form. We can easily find it with the help of Cayley-Hamilton theorem. For this solution, our matrices which is 2, 1, 1, 0, 1, 0, 1, 1, 2. Now with the help of characteristic equation, that is determinant A minus lambda equal to 0, the indeterminant 2 minus lambda 1, 1, 0, 1 minus lambda 0, 1, 1, 2 minus lambda equal to 0. Firstly, we have to finding the values of S1, S2, S3 and substituting in our characteristic equations of the order 3. Then that is characteristic equations of the order 3, that is lambda 3 minus S1 lambda square plus S2 lambda minus S3 equal to 0, where S1 is a sum of principal diagonal elements of the given matrix, that is nothing but the trace of the A, equal to 2 plus 1 plus 2, that is 5. Now S2 equal to sum of minors of principal diagonal elements of the given matrix. Here minors of 2, that is 1, 0, 1, 2, plus minors of 1, that is 2, 1, 1, 2, plus minors of 2 again 2, 1, 0, 1, and simplified 8, and that will give you 2 minus 0 plus 4 minus 1 plus 2 minus 0, that is 7. Now finding the S3. S3 is nothing but the determinant of A. A is equal to 2, 1, 1, 0, 1, 0, 1, 1, 2. Finding the determinant of 8, that will give you 3. Now substituting these values of S1, S2, S3 in our characteristic equations, then our characteristic equation is lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. Now substituting it, that will give you lambda cube minus 5 lambda square plus 7 lambda minus 3 equal to 0. With the help of Cayley-Hamilton theorem, here replace lambda by a capital A, where A is our given matrices, and our equation becomes lambda cube minus 5a square plus 7a minus 3 into I, where I indicate by the identity matrices equal to 0. That is our equation number 1. With the help of that equation, we can find the long polynomials form of the matrix representation. Here, according to the Cayley-Hamilton theorem, is equal to 0, which is already verified in earlier example. Now, we have the polynomial form, which is a raised to 8 minus 5 a raised to 7 plus 7 a raised to 6 minus 3 a raised to 5 plus a raised to 4 minus 5 a raised to 3 plus 8a square minus 2a plus I. For the simplification of that, we use the characteristic equation, that is a cube minus 5a square plus 7a minus 3i. Here, with the help of term adjustment method, we can easily identify. Then a cube minus 5a square plus 7a minus 3i into first term, which is a raised to 8. Then which term which is multiplied in a3, we get a raised to 8. Obviously a raised to 5. Then a raised to 5 into a raised to 3, that is a raised to 8. Then minus 5 a raised to 7 plus 7 a raised to 6 minus 3 a raised to 5. Then first 4 term we get easily. Plus, similarly we can written in bracket a cube minus 5a square plus 7a minus 3i. First 4 term we already get. Then which term which is multiplied, then we get the a raised to 4. Obviously a, then a into a cube, that is a raised to 4 minus 5a cube plus 7a square. But we have the 8a square, then 1a square which is remaining, then plus a square adding minus 3i into a, that is minus 3a. But in our polynomial form, that is minus 2a. Then already we have the minus 3a, but we require minus 2a. Then adding a again, then a square plus a plus I, which is remaining, that is identity matrix, then also plus I. Then simplified that term means a cube minus 5a square plus 7a minus 3i into a square plus a square plus a plus I. Here we already know the values of a cube minus 5a square plus 7a minus 3i, that is 0. Then 0 into anything, 0, that will give you a square plus a plus I. That means we have the simplification of that matrix representation of the long polynomial form, that is a square plus a plus I. Here we use the term adjustment method. You can also use the division method, means long polynomial equation which is divided with a cube minus 5a square plus 7a minus 3i, as you like, with the term adjustment method or a division method. And remainder portion, that is, if you can use the division method, then our remainder portion, that is a square plus a plus I, that is our exactly answer. Now firstly we have to find the values of a square. Then a square equal to a into a, then 2 1 1 0 1 0 1 1 2 into 2 1 1 0 1 0 1 1 2. Now with the help of matrix multiplication, in first row first column, first row second column, first third, second row first column, second row second column, second row third column, and so on. And that will give you 5 4 4 0 1 0 4 4 5. Now substituting these values of a square, a, in our equations, that is a square plus a plus I, then that will give you 5 4 4 0 1 0 4 4 5 plus our matrix A, which is 2 1 1 0 1 0 1 1 2 plus identity matrix 1 0 0 0 1 0 0 0 1. Adding these three matrices, that will give you 8 5 5 0 3 0 5 5 8. That is exactly we have to find, that is our long polynomial matrix representation of the long polynomial form, that is a square plus a plus 5, that is 8 5 5 0 3 0 5 5 8. That is exactly we have to find. This is all about the topics of the Cayley-Hamilton theorem. I hope you guys learn something from this video. If you like this video, then thumbs up. If you think that this video will help some of your friends, then do the share with them. If you want to watch more tutorial like this, then you can subscribe my YouTube channel, and whenever I upload the new video, you get the notification. If you have any query regarding this, then feel free contact me. Thank you so much for watching me.